Okay, we're recording. So let me open that up. I guess I want to go here. I'm opening up the homework right now. Maybe I should say I'm trying to open up the homework. Okay. For each compound below, decide whether cis-trans isomerism is possible. Okay, so let me give you one that is not shown there so that we can look at cis-trans isomerism. So here is a compound, CHCl double bond CHF. Okay, so with this double bond, that basically means that you're going to have a double bond between two carbons, and you're going to have a hydrogen and a fluorine attached to this carbon, and a hydrogen and a chlorine attached to this carbon. And if I draw in the lone dots on the chlorine, it's going to look like this. Now, let's try to draw the molecular geometry. We know this thing is flat. That means all of these atoms lie in the same plane. So we also know that this is trigonal planar and this is trigonal planar. So when we draw this and make sure that it is trigonal planar, we could draw it like this. So all of the atoms are in the same plane. And if I were to take my paper and lift it like this, we can see that it is indeed flat since they're all in the same plane. Now, what's to say that I could, what's to prevent me, I should say, from drawing this instead? So let's pause for a moment so that I can draw this. And let's take a look at these two molecules. Are they the same? Well, they have the same formula. They both have two carbons. They both have one chlorine. They both have one fluorine, and they both have two hydrogens. So they have the same formula. But are they the same molecule? Well, with this guy here, we've learned in this chapter that if you have a double bond, you can't twist the double bond because it breaks it. Okay, so this thing can't twist, and we can't simply turn this into that by twisting this half of the molecule. You can't do that. You would break the pi bond. So the way to find out if they are the same is to see if they have the same properties. Now this one has a molecular polarity that's going to look like this because chlorine and fluorine are very electronegative compared to the other atoms. Here, this is going to be pretty nonpolar because fluorine and chlorine are both electronegative, and you don't have the more electronegative atom on one side. If you did have to assign a polarity to this, it'd be a very slight polarity towards the fluorine because chlorine is also electronegative. So this would be slightly polar. And this one would be very polar. And notice that the polarities are different. That means they're different structures. So these guys have names. We're not going to worry about the names, but they also have designations based on the hydrogens. So if we draw a line parallel to the double bond, and we consider this a side and this is a side, if the hydrogens are on the same side, it is cis. If the hydrogens are on opposite sides, it is trans. So cis like sisters on the same side, and trans like the Transcontinental Railroad, which goes from the East Coast to the West Coast. It goes all the way across the molecule. So what do you need for cis trans? Well, we learned in this chapter that for cis-trans, you need a double bond. It turns out you can also get this for rings, but we're not going into that right now. So you can have a cis-trans for double bonds, and you need 2 hydrogens, and you have to have 1 hydrogen on each carbon of the double bond. So we have a double bond, we have 2 hydrogens. Notice this doesn't say 1 hydrogen or 3 or 4, it says 2. You need exactly 2 hydrogens and 1 hydrogen on each carbon. So this molecule has the same formula as the ones above, but it's not a cis and not a trans. So let's find out why it's not cis or not trans. Does it have a double bond? Yes, it does. Does it have 2 hydrogens? Yes, it does. Does it have 1 hydrogen on each carbon of the double bond? It does not. So it fails test number 3. So that's how you tell if something is cis or trans. Now let's take a look at one of the problems from the assignment, okay? So one of the problems has this. Okay, does this have cis-trans isomerism? Let's check it out. Does it have a double bond? Check. Does it have 2 hydrogens? Check. 1, 2. Does it have 1 hydrogen on 1 carbon of the double bond and 1 hydrogen on the other carbon of the double bond? Check. So this does have cis-trans isomerism. So this one happens to be the trans because the hydrogens are on opposite sides. How do we draw the cis? There are 2 ways to do it. This is cis, and the other way we could draw the cis would be this way. These 2 molecules are in fact the same. We've drawn both hydrogens on the same side. Okay. Does that help you out there, Harry?
Yeah, no, that helps. That helps. Thank you.
That should kind of settle the whole matter, right?
Yeah,
Great.
thank you.
Now, notice these guys here, we don't care what they are, just that they're not hydrogens. This whole answer is predicated on the hydrogens. So in fact, these could both be CH3s. They could both be CH2 CH3s. That doesn't matter. All that matters are these 2 hydrogens. Okay, how can I help you with the next problem? Anyone else? So how about this? I'm going to give you a quiz real quick. The quiz is, what are the 4 parts of molecular orbital theory? 4 parts. Try and write them down. And while you're trying to write them down, I'm going to pause because this will take you a while to think about. Okay, Harry, just because I remembered to start recording again doesn't mean that I'm going to remember next time, okay? So you keep me on my toes, please.
All right, I will make
Thank
sure
you.
to do that next
Now,
time.
for the 4 principles of MO theory, I like to go ahead and draw an MO diagram. So if you remember for the MO diagrams, on the outside, those are pi molecular orbitals. And on the inside, those are sigma molecular orbitals. And for every pair of them, the bottom one is a bonding one, and the one above it is an anti-bonding. And we designate anti-bonding with a star. So the one below is bonding, the one above is an anti-bonding. In addition, when we fill these in, these top 6 are all 2p's. And these bottom ones, these are 1s and these are 2s. And if you take a look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 MOs. I didn't count that right, I don't think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did count them right. Okay, there are 10 MOs. And the reason that there are 10 MOs is because there's 10 AOs. So here we have 2 atoms, and this atom has a 1s, a 2s, and 3 2p's, and this atom has the same thing. So we took these 10 AOs and we made these 10 MOs. And if we were to put electrons in here, we'd start at the bottom. And when we get to 2 orbitals that are the same energy, we would split the electrons and put 1 in each. Okay, so you might be wondering, why the heck is he doing this when he wants the principles? Well, the principles of MO are the number of MOs equals the number of AOs. 10 and 10. Furthermore, when we make MOs, these 2 MOs are made from these 2 AOs. So AOs of the same energy are used to make MOs. So what 2 AOs do we use to make these 2 S's? We use the 2S MOs. And what MOs are used to make these 2Ps, these 2P AOs? Furthermore, for 2 AOs, you get 1 more stable bonding MO and 1 less stable anti-bonding MO. And notice I put a star next to the anti-bonding one because that's how we designate that. And then you fill like Hund's rule. Technically, it's not called Hund's rule for this, but it is like Hund's rule, where you put the electrons in the more stable orbitals first, and if they have orbitals of the same amount or same stability, you split the electrons to 1 orbital per 1 electron per orbital before you pair them. All righty then. Are there any questions about these 4 principles? I believe that they combine these 2 in your book, and I separate them out. So I give you 4 MOs that I'd like you to know. Any question about that? If you're okay, give me a thumbs up. And these are the fewest amount of words I can use to get it across. This one you can see takes a little bit more. Now, what do the 2 MOs look like? Well, for H2, He2, all the way up to N2, you use what I call the Christmas tree. So do you see how this kind of looks like a Christmas tree? I call it the Christmas tree. For O2, F2, and Ne2, you use the paddle. So this looks more like a paddle than it does a Christmas tree. But if you wanted to, you could call this something else. You could call it the palm tree. You know how palm trees kind of spread out, except for, of course, this guy doesn't spread out at the top. It comes back in. So I call this a paddle, and I call this the Christmas tree. You should know both of those. You'll notice that here is where they are the same. And here's where they differ. So you should know both of those for the quiz and for the test. Do you have any questions about this? Or are you okay with that? Now, if you have trouble remembering these things and remembering the sigmas and the pi's, these are things you might want to write on your little 3x5 card that you get for the exam. Okay. All right. Now, since you don't have any questions about the MO stuff and the AO stuff, and I'm hoping that you have read through these things and done problems in the back of the book, as well as what I've assigned, we're going to go ahead and move on to the next module, which is gases and their properties. So I'm going to give you a brief overview of essentially 80% of the chapter in the next half hour. So gases and their properties, the first thing you need to know that the properties that we want to know about gases are as follows. We want to know the pressure of the gas. We want to know the volume of the gas. We want to know the amount of the gas. And we want to know the temperature of the gas. The variables we use for each of these are uppercase P, uppercase V, lowercase n, and an uppercase T. And the units for each, for pressure, sometimes we measure atmospheres. And the abbreviation for atmospheres is ATM. For the volume, we usually use liters, but we don't always have to. For the amount, we use moles. Remember the abbreviation for moles? For temperature, you always use Kelvin. So what that means is you have to take your degrees Celsius and add 273.15 to get your Kelvin. So whenever you're given Celsius temperature, convert it right away. All right. Now, if we look at the relationship between pressure and volume, between pressure and moles, and between pressure and temp, we see the following. So we're going to look at pressure and volume. This is going to be pressure, and this is going to be volume. And we see this, that as the volume increases, the pressure decreases. Or you could say the opposite, as the volume gets smaller, the pressure rises. So that means that the pressure is proportional. Well, actually, I'm going to draw this again. If we graph the pressure versus 1 over the volume, we get this. So this means that the pressure is proportional to 1 over the volume. Now, if we look at pressure and moles, we get the following. More moles of gas, the higher the pressure. Now, there are some assumptions here. For this assumption between pressure and volume, there's going to be no change in temp and no change in moles. Likewise here, there's going to be no change in temp and no change in volume. So when I say we're going to look at these two things, we're looking at those two changing and everything else staying exactly the same. So here, more moles of gas, more pressure. So we can say the pressure is proportional to the moles of gas. Now we're going to take a look at pressure versus temperature. So what is not changing here? Well, there's no change in moles and there's no change in volume. And here's what we find. And here, this is to reaffirm that we're looking at the temperature in Kelvin. So this means that the pressure is proportional to the temp. Now, if we combine all of these, pressure proportional to temp, pressure proportional to moles, pressure proportional to 1 over V, we can combine these all together and get that the pressure is proportional to NT over V. Okay? So whenever you have a proportion like this, you can always make this an equation by putting in what's called a proportionality constant. When we talk about proportionality constant, we can look at this. Your paycheck is proportional to your hourly wage, right? So paycheck is proportional to your hourly wage. Well, what's the proportionality constant here? It depends on how much you get paid per hour. If you get paid $15 per hour, it would be your paycheck is equal to 15 times your number of hours you work. If you get paid $12 an hour, your proportionality constant would be 12. Is everyone okay with this idea of proportionality constant? It's just some number, whatever is appropriate. Now here, unlike this situation where there are different proportionality constants depending on how much you get paid, here, there's only one proportionality constant. And it's something that we call the gas constant. So this guy right here is the ideal gas law, and I'm going to rewrite it again. Now, since people memorize things and they always do a better job when there's nothing in the denominator, this is rewritten this way. And a lot of people pronounce this as pivnert. And you can see that on each side of the equation, it's written in alphabetical order, P, then V, N, then R, then T. So it's written in alphabetical order. And this is the ideal gas law. And it's something you should memorize. Now, when do we use this equation? You use when there is no change in temperature, no change in volume, no change in pressure, and no change in moles. That's when you use this equation. So when they say, hey, there's a gas in the box, the volume of the box is blah, the moles are this, and the temperature is this, what's the volume? That's what you do. Okay. Now, let me show you some other gas laws. Other gas laws that you don't need to memorize, but you had better be able to use. So I don't really know the names of these laws. This is my guess, because I don't ever quiz you on whose law is this. But if I remember right, Boyle's law is P1V1 is equal to P2V2. So this is used when you have a gas at a certain pressure and a certain volume, and you change the volume. When you change the volume, you also end up changing the pressure. So in a problem like this, you're often told, here's P1, V1, and here's V2, what's P2? And the reason you're usually given V2 and V1 is it's easy to know the volume of the container you're using. And it's more difficult to measure the pressure, so you calculate it. Now, what's happening with the temperature when we put it from one box into the other thing? There's no change in temp, which means that the change in temp is equal to 0. And, or we could also say T1 is equal to T2. And there's no change in moles, which means N1 is equal to N2. There's Charles' law. Charles' law is V1 over T1 is equal to V2 over T2. And then there's the combined gas law. I think your book calls this the general gas law. And the general gas law is P1 V1 over T1 is equal to P2 V2 over T2. And then there's a couple of more laws like P1 how does this one go? P1 over N1 is equal to P2 over N2. And then yet there's another one where it's P1 over T1 is equal to P2 over T2. There's something like 5 of these laws that you need to know how to use. So I'm going to set this aside and I'm going to show you how to get every one of those 5 laws from one equation. So imagine this again, where you got a P1 and a V1 and a T1 and an N1, and you take that gas and you put it into a different container, and you got a P2 and a V2 and a T2 and an N2. So all 4 things are changing, okay? All 4 things are changing. What can we say about this? We can say P1 V1 is equal to N1 R T1. How come I don't have R1? I don't have R1 because R is a constant. I can rewrite this as P1 V1 over N1 T1 is equal to R. And this one I can write P2 V2 is equal to N2 R T2. And I can also write P2 V2 over N2 T2 is equal to R. So if they're both equal to R, what does that mean about this and this? It means they equal each other. This is Boyle's law. It's the combined gas law or general gas law. It's Charles' law. It's Avogadro's. And it's Gay-Lussac's. This is all 5 of those laws wrapped up into one nice and tidy equation. So let me show you how this gets you Boyle's law. So for Boyle's law, here's the following situation. You've got a P1 and you've got a V1. And here you've got a P2 and you've got a V2. N1 and N2 are equal. T1 and T2 are equal. So this is a problem where you take all of the gas, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all of the gas particles, and you put them in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the moles do not change. Now remember, when there's no change, that doesn't mean that there aren't any moles. It means that the number of moles doesn't change. And whatever the temperature is here, the temperature is here. Temperature here might be room temp. Temp here is room temp. So T1 equals T2 and N1 equals N2. If you understand what I'm talking about, give me a thumbs up. So what I'm asking you to think about is that the moles of gas do not change and the temperature does not change. And therefore, N1 equals N2 and T1 equals T2. Okay, let me show you how we use this in this equation. Now look at what I'm going to do for N2 and T2. N1 is equal to N2, so I'm going to write N1 here, not N2. T1 is equal to T2, so I'm going to write T1 here. So what happens to these? When we solve these equations, one of the things that you were taught in algebra is to cross multiply. So I'm going to do that for the cross. P1 V1 times N1 T1 is equal to P2 V2 times N1 T1. Now we can divide N1 from both sides. We can divide T1 from both sides, and we get P1 V1 is equal to P2 V2, which I told you is Boyle's law. So we got the right law to use for a problem simply by knowing that the moles don't change and the temperature doesn't change. So ultimately, how do we use this equation? I'm going to show you how to do it. The step by step, I'll write it out. That's no good. Let's try again. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. The way you use this equation is find what does not change, or in other words, what is constant. Remove it from the equation. And that's it. Find out what does not change, remove it from the equation. And you get the right law. So I'm going to write out a problem that's not from your book. And you're going to try and figure out what law you're going to use. A gas in a 2.0 liter container at 1.4 ATM is transferred to a container to a, let's make it a 0.50 liter container. What is the pressure? Okay, so when we start a problem like this, does it look like this is a volume? It certainly does. So I'm going to call that V1. And this looks like the pressure associated with that volume. So I'm going to call that P1. What does it tell us about the moles of gas? Not a darn thing. So I'm not going to write that down. And it's transferred to a 0.50 liter container. So I'm going to call that V2. and P2 is what they want. Now, when we transfer the gas from this container into this container, how much of it do we transfer? All of it, part of it, or half of it? All of it. So what does that mean about the moles of gas? They do not change. So since they're transferring all of the gas, I can get the moles out of the equation. They don't say anything about the temperature. So what am I going to assume? I'm going to assume that the temperature does not change. So I'm going to use this law, P1V1 equals P2V2. Since I'm solving for P2, I'm going to write P2 is equal to P1V1 over V2. I'm going to plug the numbers in. P1 is 1.4 atmospheres. V1 is 2.0 liters. And V2 is 0.50 liters. So this is going to go into that 4 times, and 4 times 1.4 is 5.6. 5.6 atmospheres. Any questions on how I got to the 5.6 atmospheres? If you're okay with that, give me a thumbs up. Now, I'm going to change this problem. I told you that the volume is usually measured in liters, correct? So what if this were milliliters and this were milliliters? How would this problem change? Well, let me show you. Milliliters, milliliters, milliliters cancels milliliters, we'd still get 5.6 atmospheres. So what's nice about this problem is we don't really care what the units are for pressure as long as they're the same for both before and after. And we don't care what the units are for volume as long as they're the same before and after, and we're good to go. Okay, so I'm going to write another problem out. Your job is going to be first to get the proper equation and then to solve it and get the proper answer. Okay? Okay, there's the problem. Go ahead and try and get the proper equation, then see if you can solve it. When you're done, give me a thumbs up. I'm going to pause the recording until you are done so that we don't have to have the radio silent. Okay, so in the interim, I've drawn a little diagram. So here's P1 and N1 and T1 and V1. And after we heat it, presumably since pressure is proportional to temp, or I should say volume is proportional to temp, the volume should increase. So that's why I drew a bigger bag. Now I have N2 here, but I also have over here that N1 equals N2 because the amount of gas in the bag does not change. We just heat it. It does say it's at the same pressure, so P1 equals P2. We want this V2, and T2 is 44. So if we write out the equation, and we get rid of the things that do not matter because they don't change, they would be P and N. And since we're solving for V2, we get V2 is equal to V1 T2 over T1. So we're going to use this equation to solve the problem. And let me show you where people make mistakes. So what I'm about to show you here is wrong. So this would be wrong. V1 is 2.0 liters. T2 is 44. And T1 is 22 degrees Celsius. So we get V2 is equal to 4.0 liters, and that's wrong. Who would like to tell me why that's wrong?
Because you didn't convert the temperatures to Kelvin.
Correct. You cannot do this problem in degrees Celsius. Remember, there is such a thing as 0 degrees Celsius, and a problem like this would, and there's negative degrees Celsius, right? So imagine if you had a negative degrees Celsius, you end up with a negative volume. You need Kelvin. So what we're going to do now is we're going to write this V1 T2 over T1, and this is going to be 295.15, and this is going to be 300. What's 4 plus 3? 7? And then what's 7? Okay, so I think that's 317.15. Does that look correct?
Yeah, that's what I have.
Okay, so here I'm going to show you another wrong way of doing this. So here we go. So I get this, and as my final answer, I get something that's a little less than 2 liters. Who would like to tell me why this problem is wrong? Or this answer is wrong?
Is it because it's less than the 2 liters? Or is that not it?
How about because T2 is 317, not 295?
Oh, I didn't see that.
Yeah, this is what a lot of people do. They go, hey, I'm going to put V1 on top. The natural thing is, well, I'm going to put T1 next to it. And that's wrong. So what I'm trying to ask you to do, what I am asking you to do is that when you get this equation and you plug the numbers and the units in, make sure you put the right number for the right variable. And you will be okay. But take the extra second to make sure you're putting a T2 where it asks for a T2. It is my hope that over the years of doing this, that I have saved many a student from making that mistake, although I'm not quite sure if it's true. And I get 2.1 liters. And so you can see that my drawing also led you to the idea that the volume should double, right? Because I drew a really big bag when I really should have drawn a bag that was just a skosh bigger. Okay. Something else I want to teach you, STP. This stands for standard temp and pressure. And the pressure is 1 atmosphere. The temperature is 0 Kelvin or 273.15 K. Now, there's something else I want to teach you is that pressure, the units are usually atmospheres, but sometimes they can be millimeters of mercury. And this is exact. 1 atmosphere is exactly 750 millimeters of mercury. And that is because if you have a container of mercury and you have 1 atmosphere pressing down on that container of mercury, the mercury will be pressed up the container. And this here is a vacuum up here, no gas. The mercury will be pushed up 760 millimeters. And that's where the origin of 760 millimeters comes from. Whereas if you had a container like this that had mercury in it, and you have 1 atmosphere pressing down on the outside and 1 atmosphere on the inside because it's open, the level of the mercury would be the same inside as it is outside because it's the same pressure, so the same level. The only way to get that mercury to travel up is if the pressure coming inside the straw is smaller. And definitely if there's a vacuum in there, there is no pressure pushing down on the mercury. So this is the origin of 760 millimeters of mercury. You'll notice that TV stations, when they give you the barometric pressure, they give it to you in inches of mercury, not millimeters of mercury. And guess what 30 inches of mercury is approximately? If you guessed 760, you're right. Now, another interesting thing about the barometric pressure is that the barometric pressure will change depending on your altitude. So the barometric pressure in Denver is actually lower than it is here in Eureka. It's probably a good, I'd say 5% lower. So here it might be 760. In Denver, it might be, 730 or 720 millimeters of mercury. Now, the interesting thing is when you go to the Weather Channel and you look at the barometric pressure in Denver, and it's 720 and that's normal, it's going to say 30 inches of mercury. And it's not 30 inches of mercury. It's more like 27.5 or something like that. So why do they say 30 inches when it's not? And the answer is they give you a relative pressure without regard to the altitude. So when they say, hey, it's 30 inches of mercury in Denver, what they really mean is that it's a normal pressure in Denver and 30 inches is normal. Whereas if they change the number, depending on what altitude you're at, people will get confused all the time. And the reason why they try to avoid that confusion is because most people in the business or who've taken a chemistry class know that when you have 30 inches of mercury, that's normal pressure. If it gets above 30, so 30.1, 30.2, that's a high pressure system. And what that means is that you have a lot of air being pushed out and you keep bad weather out. If you drop below 30, you have a low pressure system and it allows bad weather to come in. So when you're looking at the Weather Channel and you're looking at the barometric pressure, 30 is the cutoff. Above 30, it's probably going to be nice. Below 30, look for weather coming in. Okay, so you should know the standard temp and pressure. So now I'm going to give you another problem here. What is the volume of 1.00 mole of argon at STP? Now, there's something else I didn't tell you, but I'm going to tell you now. R is 0.0821 liters atmospheres per mole per K. But you can also use 62.4 liters millimeters of mercury per mole per K. Either of these are okay. So which one do you use? And the answer is, if you're working in atmospheres, use this one. If you're working in millimeters of mercury, use this one. So what is the volume of 1 mole of argon at STP? Go ahead and solve this. When you solved it, give me a thumbs up. And I'm going to pause the recording. Okay, in this problem, we have V1 is what we want. We have N1 is 1.00 mole. We have P1 is equal to 1 atmosphere. And we have T1 is equal to 273.15 K. Now you'll notice there is no reference to a different volume, no reference to a different number of moles, no reference to a different pressure, and no reference to a different temperature. So that means there's no change in any of these. So that means we want to use this. We want to use the ideal gas law. So when there's no change, you use this guy. When there's no change, you use this guy. When there's a change, you use this guy. So I call this a static problem, and I call this a dynamic. So dynamic, something's moving. Static, no change. So we want to use this one, and we're solving for volume. So moles is 1.00 moles. And as always, when we're doing these problems, please put your units in. Now, the pressure is 1 atmosphere, so I'm going to use this R with atmospheres in it. And the temperature is 273.15 K. So the K's cancel, the atmospheres cancel, the moles cancel, and we're left with liters. And you should have got 22.4 liters. Everyone good on that? If you are, give me a thumbs up. Okay, so we've covered quite a bit. There's one last thing I want to talk about, and it's called the kinetic molecular theory of gases. And I believe the book gives you 3 of these, and I give you 4, another one of those things. One of the first things I'm going to tell you about the kinetic molecular theory of gases is that they're mostly space. So when I draw something like this, and I draw these as gas particles, what is in between the particles? And the answer is nothing. And what do you call a volume where there's nothing in it? You call it a space. Okay. Sometimes we call it a vacuum. So they're mostly space, and that means that gases are easily compressed. Compressed means you can easily take a gas and put it into a smaller container. So here I have 1, 2, 3, 4, 5, 6, 7 gas particles. 1, 2, 3, 4, 5, 6, 7. I can easily fit all 7 into a smaller container. Gases are easily compressed. Gases mix. So if I have 2 different gases here, and for this gas, I'm going to have 3 X's, and for this gas, I'm going to have 3 O's. If I remove that center bar, what's going to happen is that the gases mix. So the X's spread out, the O's spread out. Now, why do gases mix? And actually, I gave you this the wrong way. I should say the particles move in constant, rapid, and random motion. And so here, gases mix. So the thing that's missing from this drawing is that these particles are moving. and they're moving in straight lines until they hit something, and then they bounce off. Now, if we take this partition away, do you see this little gas particle here that would hit the partition? Well, that gas particle would not hit the partition, and it would end up going to the other side. Same way with this particle here, without the partition, it would end up going to the other side. So gases mix. Another thing that we can say is that the kinetic energy, the average kinetic energy of a gas is proportional to the temperature in Kelvin. So here, what this means is that gases mix faster when hot, and they mix slower when cold. The reason for that is that kinetic energy is mv squared over 2, where v is the velocity. So when you increase the kinetic energy or increase the temperature of a gas, you're increasing its kinetic energy. When you increase its kinetic energy, you increase its velocity. When you increase its velocity, this constant random rapid motion becomes even more rapid, so they mix faster. So what does this mean if a gas is colder? They mix more slowly, okay? So you can use this to your advantage, just so that I can behave like a middle school kid again. If you fart in a cold car, you might get away with it because the gases move more slowly. Whereas if you fart in a really hot car on a hot day, everyone's going to smell it very quickly. I'm just saying. So if you understand the ramifications there of farting in a cold car versus a hot car, give me a thumbs up. You don't get it, Jackie? Okay. I thought for a minute there Jackie was going to turn her mic on and say, I don't fart. What are you talking about? Okay. So what's the other thing? Collisions are elastic. So what that means is that when a gas particle hits something else, no energy is lost. Now, that's not completely true, because when you do have collisions, you do have kinetic energy being lost through heat transfer. Okay, so how is it that we come to the conclusion that collisions are elastic? Well, if the collisions are elastic, that means a gas particle hits something and it stays a gas particle. But if the collisions are inelastic, it means a gas particle hits something and it slows down. And it's something else and it slows down. And if it keeps slowing down, what's going to happen to it eventually? It loses all kinetic energy and it drops to the ground. And when it's on the ground, what's going to happen then? When other molecules get dropped onto the ground, they're eventually going to glue themselves together and stick together and become a liquid. Okay, so the fact of the matter is that the Earth has been here for 4 billion years. It has an atmosphere and it still has an atmosphere, which means that the collisions must be elastic. Now, they aren't completely elastic. What keeps our gas molecules? And the answer is the sun. The sun does it. If we didn't have a sun, all the gas molecules would turn into liquids and eventually solids, and you wouldn't have the gas. So the only reason that the collisions seem to be elastic is because of the sun. So part of the molecular theory is that collisions are elastic. And so therefore, if there's no change in pressure, no change in temp, gases stay gases. Now, that's another thing that we can talk about is, so what would happen if you really did increase the pressure? Gases would turn into liquids. What would happen if you really lowered the temp? Gases would turn into liquids. And so here, the ideal gas law is not ideal under high pressure or low temp. So that's the last thing I wanted to leave you with the gases. We'll finish this up on Friday, and we'll actually start module 11, some of the lecture for module 11 on Friday. Module 11 is a weird one. It's a different sort of thinking. It's more qualitative than it is quantitative. All right. Thank you for listening. Turn on your mics and say goodnight.
Bye, everyone.
Bye.
Bye-bye.
Bye.